Hey guys, welcome back. Let's look at the second question of today. So the question says that Li Hua has a pattern of n cross n. Each cell is either blue or red. He can perform exactly k operations. In each operation, he can choose a cell and change its color from red to blue or blue to red. Each cell can be chosen as many times as he wants. Is it possible to make the pattern that matches its rotation by 180 degree? So we take a grid which is red and blue, which consists of two colors, red and blue. We need to print out yes if it is possible to make this pattern that matches its rotation by 180 degree after applying k operations. That means we'll be given a grid. This is a grid will be given, let's say, and is it possible to perform k operations on this grid such that after performing the operations it will be same if we rotate it by 180 degree. So that is the question. If yes, then we'll print yes. So in this case, the first case, k is equal to 0. That means no operations should be performed. And 4 cross 4 grid is given. So this is the grid. As we can't perform any operations, we'll rotate it by 180 degree. Once we rotate this by 180 degree, this first grid, the second grid is what it represents, right? After rotation. So are these two grid equal? No. So it is no. But in this case, this is the original grid. We need to change it such that after 180 degree rotation, the second grid comes. So we perform operations on this cell, this red becomes blue here, and then this cell red becomes blue here, and again this cell, 3 operations. Okay, so in 3 operations are given. We can perform 3 operations to make this original grid as equal to the second grid. Now this second grid, once rotated by 180 degree, comes out to be third grid. So second and third grid after 180 degree rotation, they both are equal. So yes, it is possible. Okay, got it? So that is the question, that will be given a grid, and after 180 degree rotation we need to make it equal. Okay, so grid, then there's a step missing. That will be given a grid, then we'll perform k operations, and after k operation we get another grid. So this grid after 180 degree, let's say this is grid A, this is grid B, after 180 degree rotation is equal to another grid which is C. So we need grid B equal to grid C. Got it? That is the question. So what is k operation? It switches a color. So red becomes blue, a cell red becomes cell blue, and a cell blue becomes cell red in one operation. Okay, and what does rotation do? Let's say we'll build a simple 3 cross 3 grid, right? So let's say A, B, C, D, E, F, G, H, I. So after 180 degree rotation, it will become, so 180, right? So it will be A, B, C, D, E, F, G, H, I. So element A has traveled here to the bottom. We'll try to see if a pattern emerges. So this element G comes here. Let's write a general. Let's say a general cell which is at position I from the top and at a position J from the left, right? This is how we write, right? We'll put up a coordinate system that it is I steps down and J steps towards the right from the topmost point, right? So let's say D is at a second position, that means 2 positions down and just 1 position towards the right. Okay, so let's assume I and J, so it is I down and J towards the right. So after 180 degree rotation, that cell, okay, so after 180 degree, that means this whole number system, this coordinate system is also rotated by 180 degree. So once we rotate this whole coordinate system by 180 degree, it becomes like this, that it is I and j, right, from this point, then from the bottommost point. So once we rotate it by 180 degree, this becomes the coordinate system, that whatever was I and j from the top left is now I upwards and j leftwards from the bottommost point. Got it? We'll generalize even more. So if now we need coordinate system, so we'll build a complete coordinate system. Let's say this is grid 0 0, right? So these are the indices, so I and j, so 0 1 2 0 1 2. So this grid is 0 0, this grid is 0 1, this grid is 0 2, this is 1 0, and likewise. Okay, so I and j is the identity of each cell, I comma j. So this I comma j, after 180 degree rotation, what happens is that the grid becomes like this. So this becomes, once we rotate it, this becomes j and this becomes I. So 0 1 2 0 1 2. So I, it goes increasing like this and j goes increasing like this, right, which was previously this, has now turned to this. But we need a general way, right? So this is how it turned out to be, but we need in the actual location according to the similar way, that from the topmost point we need I and j, from the topmost point we need I and j. Now we know the distance. Let's say we take this grid. Okay, I'll mark this green grid. We need this green grid. This green grid is at position I equals to 2 and at position j is equal to 0. So in this case, position I is equal to 2 from the bottom right part and j is equal to 0 left towards the left. So the element x is here. Now what is this position? This position according to the coordinate system which we have put in. This coordinate system has been changed to this, and if we take again the original coordinate system, which is, let's say, not I and j this time, p and q. So p comes from 0 1 2 and q again 0 1 2. This is another coordinate system which is similar as the first one. The first one has been transformed into this due to 180 degree rotation, and after 180 degree rotation, this new grid, we are applying the same coordinate system to the new grid. So now this grid, position of grid x, the cell x is 0 comma 2. Now as we have the distances I and j, we can find the coordinate system is nothing but distances, right? So we can find the distances. So this distance, that is p. What is this p? This p is nothing but total n minus I, right? Total n minus I plus 1, because this ith is the ith from the bottom, ith cell from the bottom is what we need. So what is it from the top? From the top it is n minus I plus 1. So p is nothing but n minus I plus 1. Got it? I'll rephrase, I'll tell you the statement again. The ith cell from the bottom, is n minus I plus 1 cell, 1th cell from the top. Got it? Similarly, now we take from the left. What is the position of this x cell from left? It is equal to total n minus this j part, this q part, plus 1, because this cell itself needs to be added. This self, we need the position, right? So it will be n minus j plus 1. So after 180-degree rotation, this is the transformation, that each cell with position I, it has the new position equal to p, which is n minus I plus 1, and we need the original cell I comma j to be equal to its cell after rotation. And what is its location after rotation? It is p comma q. So I comma jth cell should be equal to n minus I minus 1 comma n minus j minus 1. So this is what we need to ensure. And if it is not equal, then we'll perform an operation on this cell I comma j. And once we perform, let's say this I comma jth cell is red, right? This is red and this is blue. I'll use blue color. So this cell is blue. This is the location, right? So this is the location of a cell, and this cell is red, this cell is blue. As they are not equal, but we need them to be equal, so we need to perform an operation on them. So if we perform an operation on I comma jth cell, we'll turn it into blue, right? Because red cell turns to blue and blue cell turns to red. So this red cell turns to blue. Once we perform an operation on the cell, it matches its adjacent cell. So there is no need to perform another operation. One operation performed on a mismatching set. Mismatch. If it is red, the second is blue. If it is blue, the second is red. If there is a mismatch and we perform an operation on one of the cell, that cell becomes a matching cell, right? Because there are only two options, red blue, so turns to blue blue, or it turns to red red, right? I hope you got this. So we need to iterate through the loop, and we need to check that every I comma jth element should have the same color as n minus I minus 1 comma n minus j minus 1th cell. We need to ensure this for all the cells, and if it is not correct, if it is not matching, then we need to make an operation on it. Now that is what we'll be doing, but is this the best way? What I'm saying is that we'll take another general grid. Okay, this is another general grid. So we check this cell A with this position A. Okay, I'm just denoting the positions as the letters. We'll check B here. This counterpart, this I comma j, comes to n minus I plus 1 and j minus I plus 1, which is this cell, if you can visualize it. Okay, so this cell, the second cell, is its matching is the second cell from here, this cell. So we need to check this B, this with this B. Then again we need to check this C with this C. Let's say this T with this T. Now let's say I'll choose this E with this E. Got it? So when we check all these elements, so we come from top left to right, top to bottom, right? One by one we'll check. So this, once we go left to right, top to bottom, we are checking it with from the bottom right, right to left, and bottom to up, right? When we are checking from the top left point, from left to right, top to bottom, it is checked with the appropriate from the bottom right point, from right to left, bottom to up, bottom to top. Got it? So if you can visualize it, as we come from here, as we cross like this, right, this is crossed like this, so we are checking this. When we are checking, the two elements are checked, right? Element 1 is compared with element 2, so both the elements are compared. So to make it optimized, we just need to make it to the halfway mark, and till the halfway mark we need to find what is the halfway mark. If there is an even, okay, there's another case. Okay, so if there are even cells, right, the halfway point is if we cross, let's say we are crossing this x x x x, so this is the halfway point. We don't need to check this middle cell, because we can check, or this doesn't matter, because even if we check this middle cell, the match for this middle cell, that is if this is I comma j, the n minus I minus 1 comma j minus I, sorry, n minus j minus 1, this adjacent cell for this middle cell is this middle cell itself. So if we check, it doesn't matter. If we don't check, it also doesn't matter, right? But for all these cells, this all y cells are checked. So we just need to make it to the halfway point. And if this even, if there are even cells, then the halfway point is, let's say, I'll represent this, which x is what I'm checking. Okay, so if I check that, I'm marking it as cross. So I check this one, I check this one, I check this one, I check this one. So once we checked all this, that means we have also checked all these elements, right? So it comes like cross this one, and then this one. So we just need to make it to the halfway point. And what is this halfway point? This halfway point is such that this cell's position, if it is even, this cell's position is always greater than this cell's position. And in this case, in this odd case, they are in the same row. That means I'll mark it down. Okay, so I is equal to 1 2 3 4, j is equal to 1 2 3 4, I comma j. So we just need to compare till when the cells I, okay, this has a counterpart, this, right? I'll mark this green cell has its counterpart as blue cell. So the green cell's coordinate are 4 comma 2 comma 4. Okay, 2 comma 4, right, because it is the second cell from the top and the fourth cell from the left. Its counterpart is this y cell, and this y cell's coordinate are 1 comma 3, which is, sorry, 3 comma 1. It is 3 cells from the top and just 1 cell at the left. So this is the maximum that we're checking. This is the range till we are checking, right? From starting till this cell we are checking. What is special about this? The speciality about this is that we are checking it only till this is I comma j. This is n minus I minus 1 comma j minus I minus 1, n minus j minus 1. Let's say n is equal to 4, right? So for I is equal to 2, n minus I, 4 minus 2 is 2, so n minus 2 plus 1 is equal to 3, correct? N minus j, n is 4, j is 4, so n minus j is 0, 0 plus 1, it is equal to 1. So the counterpart of this I comma j cell is this cell. So counterpart till where, this is the maximum point, right? And we are checking it till this green cell. So the speciality about this cell is that the I value is lesser. We are only checking till the midway point. So from the starting we are going to the halfway point. Only till 2 we are going. And in the odd case, in this case, the counterpart of this green cell is this blue cell, right? But these two are on the same level. Because it is odd, these two are on the same level. So we need to compare j. So till j of x is lesser than j of y, we go on checking the cells. Okay, so that is what we are going to do. I'll show you the solution. I'll tell you why I got a TLE once I show you the. Okay, so I take the input as a array, 2D array of I comma j, and then for each cell I'll tell you why are the limits. Okay, these are the limits. I'll tell you till where. So I check if the color at I comma j, the color at I comma j is not equal to the color at n minus I plus 1 comma n minus j plus 1, then we need to perform an operation on it, and finally we'll print out the operations. But there's another beautiful thing to that. Okay, so if the operations are greater than the, these are the mismatches. So if there is a mismatch, I am increasing the counter O. Now if, let's say, there are two mismatches and there are 5 operations, so we, in this 5 operation, will make the two mismatches as the matches, and now we have made it such that this is a, let's say this is a good grid. Okay, a grid which satisfies that it is same once it is rotated by 180 degree, it is same. We'll call it as a good grid. So once we have made it a good grid by performing operation on the mismatches, there's no need to do anything, but we are still left with 3 of the operations, and we have, in the question it is mentioned that we need to perform all the operations. So we need to perform this extra operation somewhere such that it doesn't change anything, because we have already made this a good grid. What I'm saying is, this is a bad grid. And why? Because it has, let's say, two mismatch. So what we need to do is perform k operations to make this into a good grid. And a good grid is a grid which after rotation of 180 degree is the same. So this grid P is same grid P once rotated by 180 degree. But what I'm saying is, if k is equal to 5 and let's say there are only 2 mismatches and there are 5 operations we need to perform, and so we'll perform this 2 operations, right? And we have 5, so we are remaining with 3 operations, extra operations. These are extra. So these 3 extra operations should be made such that there is no change to the array, so to the grid. Is it possible? Yes, it is possible. It is possible if the grid is odd. If the grid is odd, we'll perform the extra operations on the middle cell, because the middle cell is the counterpart of this is the middle grid itself. So changing this does not change the good nature of the grid. So even if it is blue or red or blue or red or anything, okay, anything, whatever this may be, the grid is always good. If we change the middle cell, there is no problem. It does not affect the answer. So we'll perform all the extra operations on the middle cell if there are extra, okay. But let's say there is a even cell. If there is even cell, that means there is no middle cell. That means each cell has a counterpart. So this cell has this counterpart, right? Each cell has a counterpart. So if we change one of the cell, its counterpart must also be changed to make it still a good array, a good grid. No, my bad. Its counterparts must be same. Okay, this was a good grid. Okay, so this is a good grid. Same conditions, that there were 2 mismatches and we have 5 operations, and after performing 2 operations we are left with 3 operations, and this is a good grid now. But we still need to perform 3 operations. So we'll perform an operations on, let's say, this grid. So this grid is now a mismatch. Now if we again perform another operation on this grid itself, it is reverted back to what it was when it was good. So when we perform even number of operations on the same cell, the cell is reverted back to its original form. That means if it was good, it remains good. So there must be even extra operations to make a good array be good after performing extra operation, right? This condition is that the extra number of operations should be even. Got it? So these are the all the conditions. Okay, there is a lot of checking. I'll summarize it once again. So first we'll iterate through the loops. Okay, I'll write it neatly. We'll iterate till halfway point, till halfway, to find number of mismatches. Once we have found that, we need, for each mismatch, let's say we have found the number of mismatches as p. For each mismatch p, we need p number of operations, right? To make it good, we need p number of operations. So the extra remaining operations, if there are any, okay, if there are any, so if k, that is the operations, is greater than p, in this case only there are extra operations remaining. So and this extra operations is k minus p. So this extra operations, if n is odd, it doesn't matter. If there are extra operations, it doesn't matter. We'll perform it on the middle cell, extra on the middle cell. So nothing changes, right? And if n is even, then we need to make ensure that e is also even, so that this good, we are performing e operations on the good array, right? We are fixing it by using p number of operations to make a bad array, a bad grid, into good grid, and then we are performing e number of operations to make a good grid into a good grid. Okay, so for this n to be even, we need e to be even. If it is, sorry, if n is even, then e should also be even, that is extra operations. I hope you understood it. So that is what I have done here. I have counted the number of mismatches. If the cell is odd, if the number of cell is odd, okay, n is equal to 3, we just need to check if there are enough operations. If the number of operations is greater than the number of mismatches, then yes, it is possible, because we'll use all the extra operations on the middle cell. But in this other case, when there is even number of the grid is of even cross even, then we need to check if the extra cells, if the extra operation, sorry, if this extra operation is divisible by 2, if it is even, then only it is possible. And also, of course, the k should be greater. That means the number of operations should be greater. So e must be greater than equal to 0. The extra operations should be greater than equal to 0. Okay, this was the solution. So I tried this, but I got a TLE. I'll show you again. Okay, there's no need to showing, I'll tell you. Okay, I used a scanner class, and as we are inputting, not inputting, as we are taking input as n cross n grid. And what are the values of n? I'll show you. So the values of n, that means cell, the number of cells is 10 to the power 3, right? So 10 to the power 3 times 10 to the power 3 is 10 to the power 6. There are 10 to the power 6 cells, and for each cell, if I am taking separate input, the computer is incredibly fast at doing calculation, but it is very bad, because no, where it is bad where it has to take input or present an output. So when we take this input individually by cell, grid by grid, that is incredibly slow. So that gives us a TLE. So this TLE answer, I'll open it in a new tab. So this TLE answer, I just used a scanner class, and I took input slowly. This input is a general normal way, but this normal way is very slow. So I got a TLE, even if my logic is correct. So what I had to do was I had to use a fast scanner. Okay, as you can see, I'll show you. I had to use a fast scanner. This is the same code. This main function is same. I just have taken a fast scanner object instead of a normal scanner object for taking inputs. So this fast scanner object you must use. You can learn about this online. What is this? Okay. Thank you guys.